Okay, so here's our first example from the combustion analysis ALEKS topic. It says we have 4 grams of a certain compound X known to be made of carbon, hydrogen, and maybe oxygen, maybe not. And it has a molar mass of 26 grams per mole. It's burned completely in excess oxygen, and the mass of the products are carefully measured. We have carbon dioxide and water as products. Use this information and find the molecular formula of X. So before we get started, let's just look very briefly at what combustion analysis is, what it looks like. So combustion analysis of organic compounds is often carried out using a setup like this one that you see here. We have a sample of a known mass, we place it inside of this furnace, and we heat it in the presence of oxygen. And essentially, we're just combusting this sample. What are the products of a combustion reaction of organic compounds? It contains hydrogen, oxygen, sometimes oxygen. We get water, and we get carbon dioxide as products. So the carbon dioxide and the water that are produced from this combustion reaction are collected in these little traps. So here's the water absorber, and here's the carbon dioxide absorber. And these are weighed before and after the combustion reaction. And then we're able to get the masses of our products from this reaction. So that's where that information in the problem comes from. We also have a chamber here filled with CuO. This just is there to ensure that all of the carbon in the sample completely combusts to carbon dioxide. So how do we find the carbon, hydrogen content, and oxygen if it's there from the information given? We're going to use this little guide. Okay, we're going to use this guide. So I'll keep coming back to this guide here. Let's go back to the problem. So we're looking at the problem, and I see my two products. There's carbon dioxide, and here's water. We have the masses of these products. So they weighed it before and after the reaction, and they got a mass. The mass of carbon dioxide is 13.54 grams. The mass of water is 2.77 grams. The first thing we want to do is let's find the mass of carbon in this sample. So how will we do that? Look at our guide. It's going to start with the mass of CO2 produced, and we're going to go through this chain. All right, so let's do carbon first. We're going to figure out how much carbon was in our sample that we burned, what the mass of the carbon in that sample was. All right, so it says we need to start with the mass of CO2 produced. That was 13.54 grams of CO2. We need to convert this from a mass of CO2 to moles of CO2. Well, how can we do that? We need to use the molar mass, of course. So the molar mass of CO2 is 44.01 grams of CO2 per 1 mole of CO2. Now that I've divided by the molar mass of CO2, I have moles of CO2 produced. And now let's use what we know about the carbon dioxide molecule to figure out how many moles of carbon we had in our original sample. So if I write the chemical formula for CO2 here, if I have 1 mole of CO2, how many moles of carbon do I have? There's a subscript there, so I have 1 mole of carbon atoms as well. So we use that relationship here. For every 1 mole of CO2, I have 1 mole of carbon atoms. So now we are here, moles of carbon atoms in the original sample. If I stop right now and take this mass of carbon dioxide and do the math, my leftover units would be moles of carbon atoms. So I would know how many moles of carbon I had in my sample, but I'm not done. I want to go from moles to a mass of carbon. So we need yet one more conversion factor. So let me plug that in. What are we going to use to go from moles to mass? We're going to use molar mass. 1 mole of carbon atoms. Its molar mass is equivalent to its atomic mass, and that is from the periodic table, 12.011 grams of carbon. So if I stop now, let's see what units cancel. Moles of carbon cancels, moles of carbon. I'm left with grams of carbon. So now that when I do the math, I'm going to know how many grams of carbon were in my weighed sample. And so when I put this into my calculator, what I get and what you should get is 3.6953 grams of carbon. So right here, what we found is the mass of carbon in our sample. Now let's check. Is this mass greater than the mass of our sample? No, our sample was 4 grams. In that 4 grams, 3.6953 grams of it was carbon. Okay, that makes sense. As long as this isn't greater than what we had to start. Right? Now let's do the same thing, but for the hydrogen. Because combustion analysis works for organic compounds. Organic compounds, again, have carbon, hydrogen, and sometimes oxygen. So we know there's hydrogen in this, just not how much. So let's start with our mass of water, 2.77 grams of water. Why are we starting with water? Remember our picture of our setup for combustion analysis. The hydrogen is in the water. We see the H here. The hydrogen is in the water, and the carbon was in the carbon dioxide. So let's find out how many grams of hydrogen were in our sample that were burned up and used to produce water. So we had 2.77 grams of water. We're going to follow this track now. Let's find out how many moles of water we had produced by using the molar mass of water. 18.02 grams of water in 1 mole of water. Now, let's consider what we know about a water molecule, H2O. In 1 mole of water, how many moles of carbon atoms do we have? 1 mole of water, I have 2 times 1, 2 moles of carbon atoms. So the relationship here is 1 mole of water, 2 moles of hydrogen atoms. Mole of water cancels, grams of water cancels. Now, if I stop, I'm at moles of hydrogen atoms. That's not what we want. We need a mass. So we need one more conversion factor. 1 mole of hydrogen atoms. What's the molar mass of hydrogen? 1.0079 grams of hydrogen. Remember, we don't use H2 here because we're talking about hydrogen in this compound, in this sample. So we don't need this to be diatomic. Okay? We don't know the empirical formula, but we know it's not pure hydrogen. It's hydrogen, carbon, and maybe oxygen. So if I put this into the calculator, what I get is 0.309865 grams of hydrogen. All right? So now I have the mass of hydrogen in the original sample, and I've already found the mass of carbon in the original sample. So the question is there oxygen in this sample? How do we know the mass of the oxygen present, if it's present at all? Well, what we're going to have to do is take the difference of the masses of carbon plus hydrogen. We need to subtract that total mass from the mass of our sample. If there's any unaccounted for mass, it must be from the oxygen. So let's take, I'll use yellow for this one. Let's take the mass of the sample, 4.00 grams. Let's subtract from that the mass of the carbon. The mass of the carbon is 3.6953 grams, and the mass of the hydrogen is 0.309865 grams. Let's see what our leftover mass is. Our leftover mass is 0.005165 grams, and it was negative. So what this is telling me is I should have rounded these values here. I had too many decimal places, but I didn't round here. Well, I didn't round too early. I just rounded to 4 and here to 6. But if I had rounded appropriately, this would have come out to be 0. I mean, it's very close to 0, all the way out to 2 decimal places. So what does that mean? That means that our original unknown sample of compound X, we burned it. So let me go back to our picture of combustion analysis chamber here. Here's our sample. We burned it, pumped in oxygen so that combustion goes completely in this furnace. Water and carbon dioxide are produced. They're the products of the combustion reaction. The water was collected here, the carbon dioxide was collected here. We figured out how much hydrogen came from this sample and how much carbon came from this sample. And when we added up the mass of the hydrogen and the carbon, they equaled the mass of the sample itself. What that means is there was no oxygen in this sample. Now, there was oxygen in the chamber, but there was no oxygen in the sample itself. So the oxygen used to form the water and used to form the carbon dioxide just came from the air that was pumped into it. So there is no oxygen in this sample. It's purely carbon and hydrogen. And we have the masses of the carbon and hydrogen here. So now let's take these masses and determine the empirical formula of this sample. So determining empirical formula is fairly easy. All we have to do is take our masses that we have, convert them to moles, and find the smallest mole number, and we're going to make it into a whole number. So let's begin. We have 3.6953 grams of carbon. Let's convert that to a number of moles of carbon. So 1 mole of carbon, we're going to use the molar mass here, is 12.011 grams of carbon. Let's do the same for hydrogen. 1 mole of hydrogen is 1.0079 grams of hydrogen. How many moles of each do we have? Well, 3.6953 divided by 12.011 gives me 0.3077 moles of carbon, and 0.309865 divided by 1.0079 gives me 0.3074 moles of hydrogen. So I look at these two values and I ask myself, which one of these is the smallest mole number? 0.3077 or 0.3074? Well, this would be difficult if I rounded too early, but I kept 4 significant digits all the way through, and it looks to me like this one is smallest. So let's take this number, we take the smallest mole number, and we divide it by itself to make it equal to 1. And we also divide the other mole amounts by that value. So I take 0.3074 and divide it by itself. 3074. I also divide the other mole numbers by the smallest mole number. Well, let's see what we get when we do that. Here I get 1, of course. And when I take 0.3077 and divide it by 0.3074, I get 1.000976. Now, Remember from our ALEKS topic on empirical formula, it's always going to be fairly close within 2 decimal places. Here, we've got 2 decimal places of 0, so 1.00. What does that mean? This is very close and can be safely rounded to 1. So what we have just found is the empirical formula of this unknown compound. These are our subscripts, or our mole ratios for these 2 elements compared to each other, carbon and hydrogen. So the empirical formula is C1H1, which is just CH. We're not done though. This is the empirical formula. They asked for the molecular formula. So what is the molecular formula? Remember, the difference between the empirical formula and the molecular formula is that the empirical formula has the simplest whole number subscripts or whole number ratios there. The molecular formula actually gives you the exact number of atoms of each element. So the empirical formula is C1H1. The molecular formula could be C2H2 or C4H4 or C10H10. How do we find the molecular formula? To find the molecular formula, what we have to do is this. It's equal to the molar mass divided by the empirical formula mass. Okay? So, what is the molar mass of this unknown sample? Let's go back to the problem. When we go back to the problem and I check our given information, I find it right here. It says that it has a molecular molar mass of 26 grams per mole. So let's go back. The molar mass in this case is going to be equal to, right, we're looking at the molar mass, 26 grams per mole. What is the empirical formula mass? Where's our empirical formula? Here it is, CH. So let's find out what the empirical formula mass is by just getting the formula weight of CH. So carbon, we have 1, and it has an atomic mass of 12.011, and then we have hydrogen, we have 1.0079. That totals up to be plus 1.0079. That totals up to be 13.0189. So the empirical formula mass is the exact same value, 13.0189. I'm not going to round it. And the units would be grams per mole. So when we put this into our calculator, the units here cancel. And our molecular formula, we're not going to get, of course, the molecular formula out of our calculator, but we do get a number. 26 divided by 13.0189 gives me 1.9971. So I get a number here, and it's always going to be very close to a whole number. So this can be rounded to 1.99 is extremely close to 2. So what this means is I take this multiplier here and I multiply our empirical formula by this multiplier. All of these subscripts in our empirical formula I multiply by 2. So our final answer will be C2H2. That is the molecular formula.